next result is if M is proper closed subspace of a Hilbert space H, then there exists a non-zero vector Z0 in H such that Z0 is perpendicular to M. So this is very important result. So this is very important result. So what is the given part? In the given part, so proof of the theorem. So what is given part? Given part, H is a total Hilbert space and M is proper subspace of H. Then it means there exists some vector x which belongs to H but x does not belongs to M. Since M is proper subspace of a Hilbert space H, then there exists some vector x belongs to H but x does not belongs to M. So remember that this is some x vector which belongs to H but it does not belongs to M because M is the proper subspace of this. Now next, let D is the distance of vector x from M. So what is this? It is a infimum of norm of x minus y such that y belongs to M. Now from this, x does not belongs to M but y belongs to M. So it means that D cannot be equal to 0. So D is always greater than 0. Why it is greater than 0? Because x vector does not belongs to M and y vector belongs to M. So that's why. Now by the previous theorem, by the previous result, we did that there exists a by previous result, if M is proper subspace of a Hilbert space H, then there exists a some non-zero vector y naught belongs to M. So there exists a unique vector say y naught in H such that norm of x minus y naught which is equal to small d. So this is a such vector x minus y naught which belongs to D. Now suppose we named this vector as z naught. Suppose z naught which is equal to x minus y naught. So y naught is a element of M. So this is a y naught is a element of M such that x minus y naught equal to d. Now we take z naught x minus y naught. Now we know that y naught is member of M. So it means it is a member of H. X is also member of H. H is a subspace. So clearly Z naught belongs to H. So remember that this vector belongs to H. So we take some vector which belongs to H. So my claim is Z naught which is perpendicular to M. So that is my purpose to prove my theorem. And Z naught is a non-zero vector. That we know that because X belongs to M, Y naught does not belongs to M. So it means it is a non-zero vector. Now to prove Z naught, we take let y is some vector belongs to M. So what is my purpose? My purpose is inner product of z naught and y equal to 0. So that is my aim to show my result. So let I take y. So this y belongs to M. So if I take this y, it belongs to M. So my aim to prove that the inner product of z naught comma y is equal to 0. So for in general, I am taking some scalar. For any scalar alpha, so I write z naught minus alpha y, z naught minus alpha y, so which is equal to x minus y naught and minus alpha y, and this can be written as x minus y naught plus alpha y. So now this vector y naught belongs to M, y belongs to M. So M is a subspace. So it means this total vector belongs to M. So this is a y naught plus alpha y. It belongs to M. That is by definition of the vector M. Also, we know the definition of D. So what is D? D is the infimum of norm of x minus y for every y belongs to M. This values. So I can also write it as M. It means this D is less than equal to norm of x minus y for every y belongs to M. It means this condition is true for every vector belongs to M. So this condition is true for every vector belongs to M. If this condition is true for every vector belongs to M, so this condition is applicable to this vector. If this condition is applicable to this vector, so it means this implies, D is less than equal to norm of x minus y plus alpha y naught. So what is D? D is norm of x minus y naught. So this is a V, and this norm is greater than equal to this values. So if I write in term of Z, So basically it is a norm of z naught which is less than equal to norm of z naught minus alpha y minus alpha y. So this is, and this can be written as norm of z naught minus alpha y which is greater than equal to norm of z naught. So this value, if I take the square of each term, so this square is greater than equal to this term. So it implies, from this it implies norm of z naught minus alpha y square minus norm of z naught whole square which is greater than equal to 0. Suppose this is equation number 2. Suppose. Now using the property of inner product, what is the property of inner product? So this is a z naught minus alpha y comma z naught minus alpha y and minus this is a inner product of z naught, inner product of z naught comma z naught, and this entire term is positive. So this is positive. Now simplify. So very carefully simplify this equation very carefully. Now it implies, first I take z naught and taking inner product with this and then with this. So first I take inner product with this and then with the second term. So it will be z naught comma z naught. This is with this term. Now with second term, so minus z naught comma alpha y. So this is with second term. Now if I am taking this, so minus alpha y comma z naught, and again with this, first this with this, now this with this. So minus minus plus, so inner product alpha y comma alpha y and minus z naught comma z naught, this values, and greater than equal to 0. So this is a simplification of this equation. So we simplify this equation in this way. If we simplify, now this first term is cancelled with the last term. So this term is cancelled with the last term. So we leave this term at this stage. Now from this, if I take minus alpha conjugate z naught comma y. So if we take scalar from first element, then it is alpha. From second element, it is a alpha conjugate. Now from this, which is a minus alpha y comma z naught, because this is from first element. Now from this, one is from first vector and one is from second vector. So we take it as alpha into alpha conjugate. So which is a absolute value of alpha whole square into y comma y, and this is a greater than equal to 0. So in order to simplify, we get this kind of equation. If negative terms are taken on other side, so it implies alpha conjugate z naught comma y plus alpha into y comma z naught, and this is less than equal to absolute value of alpha raised to power 2 into norm of y whole square. This is y dot y, inner product of y comma y. This is norm of y whole square. So also if we are taking and this side, so this can be written in the term of minus, and this is a minus, this is a minus, plus this is a norm of y whole square. So if we taken in this way, so we have many way to write this equation. So if we are taking in this way, so we just write this norm, this inner product norm into norm, which is a norm of y whole square. So this is a norm of y whole square raised to power greater than equal to 0. Now this condition is true for every alpha. What is alpha? Alpha is some scalar. So I put alpha is equal to beta, beta is some real number, into z naught comma y. I take this where beta is some real number. It is not complex number. So I write complex number into multiplication of real number and this vector. So this, if I write this value, so what we get? So from the alpha conjugate, first it is a minus alpha conjugate mean beta real number, so it is a beta, and next is z naught comma y, and this is a conjugate into z naught comma y. So this values. Next minus. So what is alpha? Alpha is beta, and this is z naught comma y. So y comma z naught can be written as z naught comma y conjugate. This values plus this values plus this term. So absolute value of alpha raised to power 2. So this is a absolute value of alpha. So this is a absolute value of beta, number 1, and raised to power 2, and second is z naught inner product comma y, this inner product raised to power 2, that is substituting the value of this, into norm of y raised to power 2 greater than equal to 0. So I just write in this way. Now from this what we get? These terms are same, this conjugate and this same, so it is absolute value of inner product of z naught y. So similarly in this way, so it implies this is a minus 2 beta into absolute value inner product z naught comma y raised to power 2 plus here it is absolute value of beta raised to power 2. So this is a raised to power 2 since beta is a real number. So this is a beta real number. So this value can be written as simple beta. So just write it as simple beta because it's a real number, it may be. So this is a simple beta square. If it is a simple beta square, so this is a simple beta square into inner product of z naught comma y raised to power 2 into norm of y raised to power 2 is some positive number. So very carefully, now understand the next step very carefully. Now from this, if it is some positive number, it is absolute value of inner product raised to power 2, it is a positive real number, same is here and same is here, so it is again positive real number. So I take this is as A. So what is A? A is inner product z naught comma y raised to power 2. It is a positive real number. Similarly, b which is equal to norm of y raised to power 2. So this is a positive real number, this is positive real number, and this can be written as minus 2 beta a. This is the value of a plus beta square into a, and this is a b, and this term is greater than equal to 0. So a, b are positive real number. So remember that a and b are positive real number. Beta is also a real number. So beta a is common. So this value is beta a, that is common, and this value is minus 2 plus beta into b, and this is greater than equal to 0, this part, or this is true for all real number beta. So this is true for all real number beta, and this condition is called a 3. A and b is a positive number. So a is positive, b is positive. So what we get of this kind. So this can, if we are taking in this way, so we get beta a into beta b minus 2, which is a greater than equal to 0. Now, if a is positive, if a is positive, if a is greater than 0, we know that this is complex number. So it may be, the result is obviously false for all sufficient small positive beta. So hence this we have, our aim is to prove this result is equal to 0. Clear? So this my aim is, now this is, so just I repeat it again. So what is A? I just repeat. So what is A? A is equal to this inner product z naught comma y. My aim is it should be 0, right? Now this has two possibilities. Either A greater than 0 or A equal to 0, because it is positive number. If it is positive number, then it has two possibilities, either A greater than 0 and A equal to 0. So suppose A is some positive number. Suppose A is some positive number in this equation. In the equation number this. If A is some positive number, when 1 by A is also positive number. So 1 by, then it implies 1 by A is positive number. So multiply by positive number, the given equation will become beta and beta b minus 2, which is greater than equal to 0. This condition should be true for every beta. So this condition is true, should be true for every beta. Beta is some real number. Now this condition is not true for every beta. Why? Because if I take beta is very small positive number, very small positive number, suppose very small positive number, and this product should be less than 1. If I take, for example, if I take beta is from this, if suppose b is equal to 1. So just to understand, I take a general term, b is equal to 1. If b is equal to 1 and I take beta is very small positive number, suppose beta is equal to 1 by 2. So this term is positive and this term is negative. If this term is negative, then this product does not greater than equal to 0. So it means this condition is not true for small for small positive number for all sufficiently small positive number, small positive beta. So this condition is not true for small positive beta. Hence, that we suppose is not possible. What we supposed A is greater than 0, so that is not possible. If that is not possible, then the possible value of A is only it is equal to 0. If A is equal to 0, so what is A? A is inner product Z0 comma Y raised to power 2 equal to 0, this value. So it means inner product Z0 comma Y which is equal to 0 for every Y belongs to M. So what it means? It means this Z0 is perpendicular to M. Because it is perpendicular to every vector of this, so it is a perpendicular to M. So this is very important result. If M is proper closed subspace of a Hilbert space H, then there exists some non-zero vector. That non-zero vector is called a perpendicular to M. Now next result is again very important. So all the results are basically important. So this is what is the statement of the next theorem. So just if M is linear subspace of a Hilbert space H. If M is linear subspace of Hilbert space H, show that if M is closed, if and only if M is equal to its double orthogonal complement. So if M is closed, so this M is of this kind, M is equal to M orthogonal complement and then M orthogonal complement. So it is in two ways. If the given condition is right, then M is closed. If M is closed, then this given condition is right. Now prove this result. So first I take one part. Suppose first let M is equal to M and its double orthogonal complement. So what is its orthogonal complement? Again, its orthogonal complement. So by previous theorem, we prove that orthogonal complement complement of any non-empty set is closed. So by using that concept, it implies M, which is a orthogonal complement of this set. So this set is a closed set. So it is our first part, proof of first part that this M is a closed. Now the converse part. Now given is M closed and my aim is to prove that. Now converse part. So let M is closed. Let M is closed subspace of a Hilbert space H. Hilbert space H. This is closed Hilbert space H. So my claim in this case, which is equal to M, and this is its double orthogonal complement. So my aim is M is equal to its double orthogonal complement. Now, if I take X which belongs to M, so it should be belongs to this set. If X belongs to M, so by definition we know that inner product of xy equal to 0 for every y belongs to its orthogonal complement. So this is a by definition. It means x is perpendicular to its orthogonal complement, and it means x belongs to M double orthogonal complement. So I take vector from M and that vector belong to this. So it implies one thing is clear, M is a part of its double orthogonal complement. Now it has two possibilities. It means it has two possibilities. Either M is proper subset of this set, or M is equal to this set. So it has two possibilities, either this or that. So suppose M is proper subset, suppose to make contradict, suppose M is proper subset of this. If M is proper subset of this, so by previous result there exists a some non-zero vector belongs to, here Hilbert space is this M double orthogonal complement such that that is perpendicular to M. So there exists some non-zero vector Z0 and this is a equal to perpendicular to M, this values. Now this vector perpendicular to M, it implies Z0 belongs to orthogonal complement of M. Also Z0 belongs to its orthogonal complement. So Z0 vector belongs to this set and Z0 vector belongs to this set. So it means inner product of Z0 comma Z0 equal to 0. Why? Because it is perpendicular to itself. If it is perpendicular to itself, then its inner product is 0. So it implies norm of Z0 which is equal to 0. So it implies norm of Z0 equal to 0 and it implies Z0 is equal to 0. So which is contradiction. Which is contradiction. Why contradiction? Because Z0 is non-zero. Hence our supposition is wrong. Supposition is wrong. If our supposition is wrong, so what we suppose that? We suppose that it is a proper subset. If it is a not proper subset, then M is equal to its double orthogonal complement. So which prove our result.